we have studied about the shapes of s orbital and p orbital. Now we will see the shape of d orbitals. But before that, we had discussed that all p orbitals have similar shape, size and energy, and they are perpendicular to each other. Again, like s orbital, with an increase in the principal quantum number, the size of the p orbitals will increase. So, 2p is less than 3p, 3p is less than 4p, and so on. Now we will see shapes of d orbitals. For d orbitals, L is equal to 2. So, minimum n that is possible will be 3. So, 3d is the smallest d orbital. So, for a subshell 2, how many orbitals will be possible? So, value of magnetic quantum number n can be -2, -1, 0, +1 and +2. So, we write them like this. Okay, -2, -1, 0, +1 and +2, that is 5 orbitals. Okay. Now, these 5 orbitals are dxy, dyz, dxz, dx square minus y square and dz square. So, how will we draw them? For convenience, we will not show 3 x's at once. We will show only 2 x's which are required to make the diagrams more clear, nothing else, x and y. So, if this is x and y, so these are the xy planes. So, the lobes will be like this. Okay. So, 4 lobes touch each other at the origin. So, this is also called double dumbbell. Okay. So, this is the dxy orbital. Now, if we take x and z and draw the d orbitals, then this is the dxz. Now, if we take y and z, so this is dyz. Okay. So, these 3 orbitals are between the axes or in the planes. Now, 2 orbitals dx square minus y square and dz square, they are along the axis. Now, we will draw dx square minus y square. So, let us say x axis and y axis. So, dx square minus y square is along the axis. All 4 of these d orbitals have quite similar shapes, but dz square have a different shape. All these 4 were double dumbbells. but dz square is one dumbbell with a ring. So let's say 3 axes x, y and z. So dz square looks like this. There is one dumbbell across the z axis and a ring. Okay. So dz square is a dumbbell with a ring. So these are the 5 d orbitals. So these 4 have similar shapes and this is different. So all d orbitals have equal energy. So again with higher n, that is higher principal number, size will increase. So 3d is smaller than 4d, 4d is smaller than 5d and so on. Now the number of nodes. So for 3d, radial nodes will be n minus l minus 1. So 3 minus 2 minus 1. So 0. And angular nodes L equal to 2. So total nodes will be n minus 1, that is 2. Now for 4D, radial nodes will be 4 minus 2 minus 1, that is 1 radial node, and angular nodes will be 2. So total nodes n minus 1 is 4 minus 1, so 3. So we are also getting 3 by adding these two. So like this we can calculate the number of nodes for any given orbital. Now we have discussed the shapes of various orbitals. S is spherical, P is dumbbell, and in d orbitals 4 of them are double dumbbells and dz square is a dumbbell with a ring. And we have also discussed how to calculate the number of nodes and how the size of them vary. Now we will read about the energy of orbitals. Now the energy calculations for hydrogen atom and for multi-electron systems are quite different. Energy of orbitals. Now for hydrogen atom, there was number of electron was 1, which was present in the 1s orbit in 1s. Okay. We will study about the electronic configuration later on, but for now the energy values of the orbitals in hydrogen atom was only depended on n. Okay. So 1 is less than 2. So if n1 is less than n2 in energy, then in 2 we know there are 2s and 2p. So for hydrogen atom, 2s and 2p had same energy. Same for 3s, 3p and 3d and so on. Now orbitals having same energy are called degenerate. Okay. So in this case 2s and 2p are degenerate, 3s, 3p and 3d are degenerate. Okay. But for multi-electron systems, energy depends on both n and l, that is both principal quantum number and azimuthal quantum number. Now, in case of hydrogen atom, 1s had the lowest energy. So, for hydrogen atom, 1s has lowest energy. This is known as the ground state. Ground state is most stable. Okay. And other levels such as 2s, 2p, 3s and so on, they are called the excited states. So, the ground state has the lowest energy and excited states have more energy as compared to the ground state. But for multi-electron systems, the case will be different. Here we had seen that in a principal quantum number, the different types of subshells, that is S, P, D, etc., had same energy. But for multi-electron system, P, D, S, S, P, D, F all have different energies. Even for same principal quantum number. Okay. Why this is the case? Because in hydrogen atom there was only one electron, right? So, the only force that was present within an hydrogen atom was the force of attraction between the nucleus and the electron. There was no force of repulsion. But for multi-electron systems, there are many electrons. Now, all the electrons are negatively charged. So, along with the force of attraction between the nucleus and the electrons, there will also be repulsive forces between the different electrons. So, these force of repulsion can be between electrons in the same orbit and also between electrons in different orbits. And also in a multi-electron system, since the lower orbits are filled with electrons, so the outer shell electrons will receive less force of attraction from the nucleus due to shielding effect. So, in multi-electron system, the energy is different due to two factors. The first one is repulsive force between electrons, and the second one is shielding effect. What is shielding effect? The electrons in the outer shells get less force of attraction from the nucleus as compared to the inner shell electrons. So, we can also say that the inner shell electrons shield the outer shell electrons from the nucleus. Okay. So, Let's say 1s orbital is nearest to the nucleus. So 1s receives the highest force of attraction from the nucleus. The next orbital is 2s. Okay. So for the force of attraction to reach the 2s, there is 1s in between and there are electrons. So the electrons in the 2s orbital will receive comparatively lower force of attraction from the nucleus than the 1s electrons because of the electron cloud of the inner orbital. This is called the shielding effect. Now the shielding effect of s, p and d orbitals are not the same due to the different shapes. S orbital is spherical, so it is symmetrical. So the electron density is equal in all directions. Therefore, the force of attraction is equal and also the shielding effect of s orbital is much higher. But for p orbitals, the electron density is in the lobes, and the spot where the lobes touch each other, the electron density is 0. So at that point, there is basically no shielding effect. So the shielding effect of p orbital as a whole is much less than the shielding effect of s orbital. Similarly, the shielding effect of d orbital is less than that of the p orbital. So shielding effect of s is greater than p, greater than d, greater than f, so on. Now due to these two factors, the nuclear charge effects. Force of attraction depends on the nuclear charge. So for 1s, it receives the direct force of attraction. So nuclear charge is Ze, that is the original nuclear charge. Okay. For other orbitals, due to the shielding effect, there rises a term called effective nuclear charge, which is expressed as Z effective into E. Now, we have said that for multi-electron system, energy depends on both N and L. Now, there is one N plus L rule for this. Lower value of N plus L means lower energy, even if the principal quantum number is lower, such as for 3D and 4s. For 3D, N plus L will be 3 plus 2, that is 5. For 4s, N plus L will be 4 plus 0, that is 4. Therefore, N plus L for 3D is greater than 4s. So, energy of 3D is greater than 4s, even though it has the third orbit and this has the fourth orbit. Then also energy of 3D is greater than 4s. Now, for same value of N plus L, lower N will mean lower energy. Okay. Now we will see the N. So, for 3D and 4P, 3D has 3 plus 2, that is n plus l is 5, and for 4P also n plus l is 5. So, same n plus l. Now, here since the principal quantum number of 4P is higher, so the energy of 4P will be greater than 3D. So, we have studied about the shapes and energy of the orbitals. In the next lecture, we will study about the electronic configuration. Thank you.